So we are going to look at a 5-switch enumerator. What that means is that we are going to have 5 switches and we need to use a 3-bit counter in order to add up the number of switches that are on. One of the ways to do this problem is to break it up into stages of how you want to accomplish it. So there's the 5 switches. It'll need to be turned into a binary input. This will need to be turned into a display on the 7th segment for the DE0 board. So we can think of the switches as S0, S1, S2, S3, and S4. So then we can have 0, 1, and up to 5 switches on. And then as for the 3 bits, we can have any values from 0, 1, 2, 3, up to 7. But we know we're not going to have more than 5 switches on, so we only need to go up to 5. Then, once it is turned from the number of switches on into binary, it will go through a small decoder function, which is what will turn it from binary to the 7-segment display. Okay, so now we are on the first block of what we broke our problem into, which is turning the 5 switches into binary. So what you do is you make a truth table with S0, S1, up to S4, and then the 3-bit counter. This would go from 0 to 31 because you have 5 switches, so you have 32 different possibilities of being on or off. And then, so here we have no switches on, here we have switch 4 is on, so we go 1. Again, we have 1 switch on, so 0, 0, 1. Here we have 2 switches on, so we're going to go into the 2's place, because there's binary over here. Here we again have 1 switch on, and then you continue all the way down. Here's at the bottom where we have 4 switches, and then we have 5 switches. And then from here, we're going to go into our different Carnot maps in order to create functions for F0, F1, and F2. Okay, so you just saw all the entries for the 32 section truth table. So here are the Carnot maps for F0, F1, and F2. And what these expressions are going to do is describe how the switches are working in binary so that we can feed it into our decoder. So here's F0, or part of it. This is the first Carnot map. As you can see, it's a checkerboard, which is super inconvenient. And then if we go over here, this is the other part. This is also a checkerboard, which again is inconvenient because we can't get any groupings. So what that leads to is F0 equals a bunch of terms plus a bunch more terms, and it ends up being that there are 16 terms for F0. And we do this process again for F1 and F2. So we just found the binary representations for the number of switches on, and now we're going to kind of create the decoder to display that on the 7th segment. So here are the number of switches that can be on, 0 through 5, and then 6 and 7 don't cares because we're not going to count up to 6 or 7. Here's the binary representation, and then here's how it will look on the 7th segment. So in order to create the code necessary to display it on the 7th segment, either look at a table in the book, or in order to create the table, you can use this here, and then look to see everywhere where A shows up, so in 0, 2, 3, and 5, and then you can put a 1 in those places, so 0, 2, 3, and 5. And then you can do the same for all the other letters, B, C, all the way up through G. And then once you've done that, you will make a Carnot map for A through G, and then that will tell you the functions you need to use for your decoders to turn your binary inputs into the 7th segment display. An important note is that when the DE0 board is given a low value, that is when the display is turned on. So we'll actually need to put a not in front of these functions. So instead of A, you have A equals not all of this. Okay, so as you can see, once you've gotten all the functions into the DE0 board, you can count the number of judges that are going to be voting. And then you see the other switches don't do anything to it. So we know it's working.
Ring, 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 banana phone.
Part 2 of the project, the hierarchical multi-level. It's a very similar procedure to the first part. except how we're breaking things apart is quite a bit different. So actually over here, so instead of using all 5 switches, we're going to split it into 3 groups of 2, 2, and 1. You could also do it of 3 and 2, but that's just not the way I did it. So you start off with 5 switches, but we're going to combine them in groups. So switch 0 and 1 are a group, switch 2 and 3 are a group, and then switch 4 is all by itself. When you just look at these 2 switches, you can either have 0 switches on, 1 switch, or 2 switches can be on. And the same for this one. And then this is just on or off. What we need to do is we want to change it into a binary representation so that we can eventually feed it into our program. So what we're going to do here is this one is going to turn into x0 and x1. And what we need to keep in mind is that this is going to be the 2's place and this is the 1's place. And remember, this is 2 2-bit representations for these 4 switches. This is what a example truth table would look like. So here 0 switches are on, so we have a 0 in binary. Here 1 switch is on, so we have a 1 in binary. Here 1 switch is on, so we have a 1 in binary again. And then 2 switches are on, we just have a 1 here. We don't want to put a 1 here because that would mean 3 switches are on, which is not possible here. So we're going to do that for both of these, and then we make Carnot maps for each one in order to get a function of x0 and x1 in terms of s0 and s1, and then another function of x2 and x3 in terms of s2 and s3. This one doesn't actually change. It's already sort of in binary. It's just to really emphasize that it's in binary and not a switch anymore. The next thing we need to do is create a 1 3-bit binary representation to combine these 2. So we'd go through the same process where we would have these would be on the left of the truth table. So we'd have it here where we'd have our x's and we'd have our y's. And then we'd create the truth table based on that. And then so we'd have our y0, y1, and y2. Then we'd feed that and this last switch into functions for f. So at the end, what we're going to have is a function f2, f1, and f0 in terms of y, which are actually in terms of x, which are actually in terms of s. So now we're back to where we want to be. So we just said that we have f2, f1, f0 in terms of s through these intermediate steps. Then the next thing would be that we want to have this display on our DE0 board. Luckily, since we already did the functions for it, our 7-segment display is exactly the same. We don't have to change anything. We already found functions for displaying the different components of the 7-segment decimal, decimal in terms of f2, f1, and f0. So we can plug it directly into our code and then get our board to work exactly the same as before.
Phone. Ring, 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 banana phone. I've got this feeling so appealing.